Okay, thank you, the chairman, for the introduction, and thank you very much for the conference to invite me here, and thank you very much for all the audience here to attend this 3 days conference. And today I'm honored to present about what we have done in recent several years about how to use the generative AI to do the building structure design and optimization. And this work is done by me, and all the names below are my PhD students. Okay, so this is online for my research presentation today. So number one is why we do the research, and number two is some key concept about the generative AI, and number three is about how we do the design, and number four is how we do the optimization using AI, and number five is how we use this technology in the real world projects, and finally we go to the conclusion. So first I come to the background. So now all this building design or structure design are very labor intensive. So architecture do the architecture design, and our engineers do the structure design. So this all this work is done by humans. So the engineer is very exhausted, and how to improve the productive efficiency is a problem not only in China but also in the United States and many other countries. So currently we are facing a critical challenge. First is that our efficiency is not good enough. The owner always wants to deliver the design result as quick as possible, but we cannot satisfy it. The second is that we have a lot of design drawings, but all of design drawings are located in the store warehouse, and we don't use it as good. And also that the design quality is highly rely on the engineer's ability, and the junior engineers cannot deliver a very good design. So we think that, okay, we can use generative AI firstly to increase our design efficiency, and secondly, we are not only rely on the experience of engineers itself, but we can make it become a fixed asset of the company, and also we can improve the design quality for the junior engineers with AI. So the second is about the key concept and technology. So firstly is what is the meaning for the intelligent. And I like the idea in the Oxford language that the importance of intelligence is that we can actually let the computer to learn something, or people learn something. So now we have many very good like parametric design software, but in this software, all the objective function or the boundary function are defined by human, and the computer cannot improve the program by itself. So that means the computer cannot learn it by itself. So we want to try some algorithm that actually let the computer to do the learning. So that is, I think, the very important concept for AI. So then what is the generative AI? So here is the animation that we found in the literature in 2017. I think this is a very good example meaning for the generative AI. So you can see that there are the faces. The bottom 4 faces are generated from the top 4 faces and the left 4 faces. So it represents 2 key characters of the generative AI. The first character is that the AI can, after learning sufficient data, it can generate something totally new, like the people on the bottom. It is a new people, it's not the real world people. The second character is that the capacity of AI is so powerful that when it generates something, you cannot identify it is generated by AI or it is the real world people. So this is 2 characters of this generative AI. So in 2017, when we see this animation, I think that, okay, it will be a revolution for our industry. Why? Because in the computer field, no matter it is an image of people's face or a drawing of a structure design, it's almost the same thing. So if a computer can generate a human face that looks as real as a real world people, why cannot computer generate a design drawing that is as good as an engineer design? So that is the fundamental idea of our research. And also there is a lot of algorithm about how to generate an image or drawing. And we use 3 algorithms to generate the design drawings. It is the first one is the generative adversarial network GAN. The second is the graphic neural network. And the third one is the diffusion model. And this is all the equation for the model, but I don't want to go to the equations. I just want to give a fundamental concept of what they are doing. The first algorithm is the GAN. It works like this figure shows. So it has 2 neural work. One is neutral network called a generator. It is like this bad guy. He always want to generate some fake image based on the real world image. And another neutral network is the discriminator. This one, like the policeman. It will identify the image you give to him is a computer generated or real world image. So if they identify this is a computer generated image, the generator will go back to optimize its parameter to improve their generation capacity. And if the discriminator fail to identify the fake image, it will optimize its parameter to give a better identification capacity. So they fight against each other, and finally, the neutral network can generate an image as good as the real world one. So that is the very similar to what we pursued for the AI to do. So we give the AI the real world design joining, and the neutral network try to learn how to generate a design joining look as the real world engineer's joining. Then that is what we pursued, that computer can really to do the learning and can upgrade its capacity. The second is about the graphic neutral network. The graphic is something made with the node and edge. It is good for represent some low equivalent data, and the GNN is a neutral network to predict some of the relationship between this node and edges. So one of the key algorithms we are using, we call is the edge classification problem of GNN. That means if we have two objects, can you identify the relationship between these two objects? So we all see the movie of Lord of the Rings, so we can see all these people there, and we can identify, okay, these three people belong to the wizard side, and this one belongs to the enemy side. So that is the fundamental idea of the edge classification problem. So what this algorithm can do, we can use it for a layout of the frame bins. Actually, there is a lot of frame columns, and we can assign links between these columns. But some of the links are the real-world bins we need, and some of the links are not real. We don't need it. So we can use the AI to do the learning, and then they can identify, okay, put all these links we need to be red, and the links we don't need to be blue. Then we can finally get the layout of the bins. And finally, the diffusion model. The diffusion model is that the AI removes noise from the picture, and you can get a more and more high-resolution picture. So we can see that if you have a white paper, you can look at as a joining full of noise. And if you remove all the useless noise from the white paper, and finally your color you get is actually the design joining you need. So this is the three fundamental algorithms we need to do the generative design of structures. And also, we need the optimized algorithm because that AI generated design, sometimes its quality is not good enough, and also sometimes our training data is not good enough. So we need to improve the generated result of the training data. And why we think about the intelligent optimization is that currently we have very good optimization algorithm, but we want to go further, that let the algorithm have the capacity to do the learning. Why? Because we have already connected a lot of data, and the generative AI can also generate a lot of data. So we can use this data to improve the optimization capacity of this algorithm. Okay, so then go to how we do the generative design algorithm. The first is that we need to, just now Professor Gu have a very good presentation that for the AI research, the most important thing is the data. So firstly, we spend quite a lot of time to connect the data, and now we have the largest structured design data set in the world. And then we propose the algorithm for the design of different components, like a vertical component, horizontal component, the cross-sectional design of different beam or column or shear wall, and also some special component design, like the base isolation for the earthquake design. So I will go one by one. So firstly, about the vertical component design, for example, the layout of the shear wall in the structure. And the interesting thing for the AI research is that when you're facing a problem, you don't know how to do with it, you can go into the real world. You can see how the real world engineer do the job, and then you make the AI to follow their steps. So how the real world engineer to lay out the shear wall. So this is like this way. Firstly, the engineer gets the design requirement. For example, the layout of architecture, for example, the floor plan, also the design condition, for example, the seismic design load of that area. And for the first step, the engineer will lay out the shear wall located in the position what the architecture permitted them to do. For example, they cannot lay out a shear wall in the middle of the room. And for the next step, they will adjust the layout of shear wall following the design condition. For example, if you have a higher seismic design intensity, you have more shear wall. Otherwise, you have less shear wall. And finally, you do the calculation to make sure that your layout shear wall satisfies some mathematics or mechanics requirement. For example, your inter-story drift ratio should be small than the limit. So we let the computer to follow all these steps. So first, for the first step, we need to let the computer to learn how to lay out a shear wall at the permitted location. So we proposed, as I mentioned, that the different algorithm to lay out the shear wall following the architectural design based on the generative GAN, CNN, and diffusion model. All the details are listed on the bottom with the paper. I cannot go too much detail of that. And here I just show the result. Okay, so on the top, on the left, two architecture design. So the green means window, the gray line means the wall, and the blue line means the door. And on the right is the layout of shear wall. The red line means the shear wall. So can you identify which one is done by AI or which one is done by engineer? So here is the result. So you can see this is what we done use AI. We do it in 2019. So you can see they are very like to each other, but if you go to detail, you can still see, okay, for example, for this location, the AI design is still a little bit different from the engineer design. And that's what we did last year with the diffusion model. You can see that the AI design is almost identical like that one in the engineer design. So that is what we purpose, that we pursue, that the AI can generate some design that you cannot identify it from the real world human design. Okay, then we say for the second step, we need to make the design condition, for example, the seismic design requirement to the shear wall layout. So we propose to use this algorithm, we call the design condition fusion in the feature space. So we get the image and the design condition, for example, the design intensity and the height together to generate training data to train the AI to learn how to embed the design condition into the generated result. So here is the result we get. So this is the architectural drawing. So if we want to design a structure with the seismic design acceleration of 0.1 g and a height of 30 meters, the AI will generate a shear wall design like this one. So you can say, okay, I don't like the building to be 30 meters, I want to be to 100 meters, and you change the design condition, and 5 seconds later, AI will generate a design like this one. And you can say, okay, I want to increase the seismic design intensity from 0.1 g to 0.2 g, and another 5 seconds later, AI will generate a result like this one. So you can see clearly that AI can connect your design requirement, design condition with the final generated result of the structure design. And then we go to the third step, how we embedded the physics model into the AI generated figure. We propose the algorithm to embed the physics requirement into the GAN. So on the top, it is the discriminator to identify, okay, this AI design result is how similar to the human design. And on the bottom, we use a physics estimator to check if the AI design result can satisfy the mechanics requirement. And we use a ResNet to neutral network to be a surrogate model for the physics estimator. And here is the result. For example, for this tall building with 98-meter height, this is the engineer design. So if we don't embed the mechanics inside, the AI generated result have less shear wall on the x direction. But when we embedded the mechanics in the AI, it can generate the shear wall more similar to the engineer design. And at the same time, we can clearly see that with this mechanics enhancement, the AI generated result can satisfy the inter-story drift limitation, while the data-driven design cannot satisfy that. So we can see that we can embed the architectural design, the design condition, and also the mechanics requirement into the AI generated result. Okay, then we go to the next step. We will do the horizontal component design. That is the layout of the beams. So as I mentioned before, that we can let the layout of beams become age classification problem of GAN. So AI do the learning and know, okay, some location we need to arrange a bin, some location we don't need to arrange a bin. But we checked and we found that existing GAN algorithms cannot satisfy the requirement. So we proposed the age feature enhanced GAN called graph SF. You can see this is the layout column. The existing GAN algorithm cannot lay out bins correctly, and our algorithm can generate a layout identical to the engineer design. So here is another two example. So on the left, these two figures is the layout of the column, and on the right are the layout of the bin. So can you identify which one is generated by AI or which one is generated by engineer? Now here the result. The AI generated layout of bins is about 95% similar to the engineer's design. And we also improve our algorithm to lay out the bin following the diffusion model, because that when we lay out the bins, it's not only related to the layout of the column, but also related to the arrangement of the floor plan. So you don't want, in many cases, you don't want a bin just located in the middle of your room. So that is the advantage of this diffusion model. It can easily to represent the plan space arrangement of your floor. And so we propose architectural spatial structure information combined into the generative into a diffusion model as the input condition. And we also proposed a mask and a gradient integrate constraint generative AI. It's very easy to remember that we call it a magic generative AI, that we can control the location of the bins that are generated by the AI algorithm. And here is the result. So for the regular frame, the AI can generate the bin layout identical to the engineer design. And for some irregular layout, and AI can generate a result either very similar to engineer design, and in some cases even better than the engineer design. So you can see that for this case, the engineer design, we cannot arrange the main bin between these two irregular parts. So you can see the structure was separated to two parts, and the integration of the structure is not good enough. But AI can directly use the main bin to connect these two buildings to make the structure have better integrated performance against the hazardous disaster. And also we can combine the shareware design and the bin design together, because that is interesting that when we training the student, so I training them one by one. So the number one PhD student working on shareware and number two student working on the layout of the bin. So after that, I read a lot of papers that they separate the layout of shareware and bins, but it is not reasonable. So when engineer design do the design, they lay out the shareware and the bins together. So we propose an algorithm to do the layout of shareware and the bin at the same time, because otherwise they cannot fit very well with each other. So this is the algorithm we proposed. The critical of this algorithm is that when you lay out the shareware, actually the flexibility of shareware layout is quite fixed, because you can only lay out the shareware on the wall position given by the architecture. But when you lay out the bin, you have a lot of flexibility, because the possible location of the bin is quite flexible. So we need to propose an algorithm to control the searching space of the bin layout. And then this is the algorithm we proposed. And this is the result. We can see that if we do the co-design, the shareware layout and the bin layout is more similar to the human design. But we do it one by one, you can see that the shareware and the bin layout is worse. And also the performance of structure is also not good enough. And then when we finish the layout structure design, and then we need to predict the cross-section. In 2022, we proposed an algorithm to predict the cross-section of columns and shear walls based on GAN. But this algorithm has limitations that it cannot be used to the design for the bin section. So we want to propose an algorithm can design both for columns, bin, and also slabs. And when we do the work, the problem is that actually you're looking at this plan layout of the structure, you found that the area of the column, the area of the bin, and area of slab, they are quite different. So the slab occupy a lot of pixels than the pixels occupied by column. So if you directly input this image for the AI to do the learning, it will more concentrate on the slab and forget everything about the section of columns. So you need to specially consider that the different proportion of the pixels of different components. So firstly, we still use we call it the mask algorithm to embed this design condition. For example, your column concrete grade, your the load, and all this information into this training data. And also we use this algorithm to that the column at the slab and at the bin, they control their proportion of these pixel numbers so they can learn together. And then here is the result. We can see that, okay, our AI generated cross-section is about one model to the engineer design, and is very efficient, much quicker than this optimized algorithm. And all this section design based on diffusion model still have a limitation. That is that if you have a concentrate load on the component, it is very hard to consider that, because how you can represent a concentrate load on an image. So we also propose a cross-section design based on the GN to consider the loading path condition and also the concentrated load condition. So this is the fundamental of the algorithm that we use the GNN to represent different components. And the key information here is we call it heterogeneous graph representation, because the bin-to-bin connection, bin-to-slab connection, column-to-slab connection, all these connections have different structural data structure. So you need to consider them separately. And here is the result. So that our section prediction with GN has also a very good result and very efficient. And because this section prediction by GN and by diffusion model are finished by two different students. So they always debate with each other which model is better. And here is our conclusion. So if your structure can be represented with an image, like all the stories have a regular arrangement, the diffusion model has a better accuracy. However, if your model, your building is irregular, for example, that you have this inclined column so that you cannot represent by different layers of image, then the GN will be the only solution for them. And then we can also do it for some special component, like the isolator on the bottom of building. Like many countries like Japan or China, because of the strong earthquake, they put the isolator on the bottom of structure to protect the structure against the earthquake. And how to design the isolator on the bottom structure is also challenging. And we propose the algorithm to do that. And we not only need to make the design similar to the human design, make the isolator satisfy the code and mechanics requirement, and also make sure that the isolator can satisfy some empirical rules. For example, all the isolators should have the same direction, similar direction, diameter. Otherwise, the deformation capacity with larger isolator will be limited by the smaller isolator. And also, we want that this all lead bearing should be on the outside of the structure, and the natural rubber bearing in the middle of the structure to make full use of the lead bearing torsion capacity. And here is the result for this tall building. Here is the layout of the isolators. All the isolators have 700 millimeter diameter, satisfy our requirement. The green one means the lead diameter bearing. It is located at the outside, and the red one means the natural rubber bearing in the middle. And all the mechanical performance of the bearing satisfy the code limitation and not too conservative. And the design speed is much, much faster than human design. And we can also use it for some retrofitting design. For example, for some frame structure, we want to place some braces in the frame to increase their seismic performance. But how to arrange the brace? We have two limitations. Firstly, we need to satisfy the architectural requirement, and also we need to satisfy the engineer or structural requirement. And the architecture requirement is very complicated because it relates to the function of the structure. So we separate this arrangement to two steps. For the first step, we need to satisfy the architecture requirement. So we use AI to do the job. We connect more than 100 design drawings and net architecture to tell us, okay, this location can arrange a brace and this location cannot arrange a brace. And then we can let AI to learn where they can arrange a brace. And then we use the structure optimal algorithm to improve the computational efficiency. Okay, so here is the result. So this is the architecture layout. For the step, all the red part is the architecture permitted to arrange a brace. And on the bottom is the final location, arrangement of brace. And the structure can satisfy the code requirement. Okay, I need to be quick, Kelly. Then we can also use it for the optimization algorithm. As I mentioned that we can use AI either as a surrogate model to improve the evaluation speed. And another interesting is that when we finish all the optimization, we don't just move to the next case. We put the optimized structure back into our training data set. So our training data set will become bigger and bigger, and the AI will be more and more powerful. And for example, how we predict the material usage when we use in the optimization. We can also use the software to do the calculation, but it will take several minutes to finish one material consumption calculation. So why we cannot use AI like a very experienced engineer to predict the material usage with only a glance? So here is the key technology that we use graphical representation to present the structure. So we can use the age of GAN to present the macro scale, for example, the component size. We can use the node and age topology to represent the structure layout topology, and also use the global feature vector to represent the design condition. So we can use a GAN to present the entire structure information. And then we can need to training AI. That is the advantage of with generative AI. In old days, when we need to train AI, we need to connect the design journey. Maybe we can connect several hundred design journeys. It's a very hard task. And now we can use AI to generate the design. We can use AI to generate 4,000 design journeys. And we use the 4,000 design journeys, we calculate the material usage, and use these 4,300 cases to training AI. So we'll be making our much more powerful. So here the result, our model is more accurate than existing models, and then we can predict the material usage with only 0.36 seconds. It's about more than 500 times faster than the design software. Similarly, we can also use the technology to predict the structure formation. We have this, we can train the AI with more than 1,000 cases, and then use these cases to train AI to generate the interstory spring stiffness, and then we use the interstory spring to generate the MDF model to predict the interstory behavior. So we can make our model also accurate than existing models and also much more faster than existing ones. So then with this surrogate model, we can use it to do the structure optimization. For example, this is the AI generated result. Its in-story drift ratio is not good enough, and then we can use the AI to do the optimization, and in 10 minutes, the system design can pass the design code requirement. But in the traditional way, even you give them 2 hours, they can also cannot do that. And also we can include enhance the data for our training, because no matter how many data you connect, it's very hard to find some design drawing that the building are designed in very strong seismic design regions. So how we can increase the number of data for that case? So that is our solution. Firstly, we use the generative AI to generate the design for some rare case, very limited data case. Of course, for this case, the first batch of AI generated result is not good enough. Then we use our optimization algorithm to improve the quality of the design. And after each, we can use this optimized result back to the training data to get a better AI design result. So we can use this method, we can increase the real data class by 7.5 times very efficiently, and AI can generate a result much better than the existing way. Okay, then when we finish all these algorithms, we don't want to just publish papers, we want to be used in real world. So we developed a software called AI Structure Copilot. It is actually it looks like a plug-in in AutoCAD. So any engineer, he can use AutoCAD. He can use this software. So he uses CAD to do a pre-process and upload their design requirement to our cloud, and cloud finish the AI design and send the result back. So it is free. You can directly download the result from this software from this address. So in just 1 minute, the AI will generate 3 or 4 different design schemes, and also with material usage, bin layout, cross-sectional design. And if you are not happy with the AI design result, you just do 1 click, the AI will generate and optimize the result about in 3 minutes, and make the structure have better structure performance. So here is a typical example. So you can see that this is the engineer design, and all this is AI design with different algorithms. You can see there are some difference, but all of these design results are very close to the engineering result. And also, our AI design result is can satisfy the design code requirement. Here is a check result of all these design indicators, and also the AI design result. Their material consumption is very close to engineer design. So this is very important. Otherwise, if your AI design result is too expensive, and the owner will not use it. And this platform has been used by hundreds of design institutes, and have already been used in real design more than 3,000 cases in the real world. So if you look at AI as a real world engineer, it designs more results than any engineers in the world now. So here is a case when I prepare this slider. So this is number 3,118 case designed by AI. It is finished at this time, and this is the designed shear worth. Okay, then come to my conclusion. I need to mention that this is something like the frame principle. So if AI can generate a drawing, generate photo, AI can generate a drawing. And if AI can generate a building drawing, why AI cannot use to generate like an infrastructure drawing or equipment design drawing? So we can further expand this technology to many, many different disciplines. So this work is we done together with Hong Kong Polytechnic University. I think Dr. Lu is here. And we can use it to the design of the sprinklers in the system, in the building. So we need to fight against fire, so we need to arrange the sprinklers. And the sprinkler layout is very similar to, I mentioned that the layout of beams or layout of shear walls. So we can lay out the sprinklers as good as the engineering design, but much, much faster than the engineering design. And we can also use it to predict, for example, the expanding of the smoke and the fire in a building, so that we can predict the slot density or temperature in a fire case, and it can make it much faster than the safety calculation. It's very important for the engineers, because when engineer design, they don't want to wait for 10 hours to get a result. They can, 5 minutes can get the result, then it can iterate their design very quickly. And we can also use it for not only for buildings, but also infrastructure. This is what we do for the design of dam. So you have a design a dam, you need to design the cross-section of a dam, and we use a similar technology to predict the design of a dam. The result is very similar to the engineer design, and also that much more efficient than the engineer design. I think there is still many, many fields that we can explore following this idea. And here is some of the awards we have get in recent years about this technology. And we think that we are approaching to a very important time for the AI design, because you can see that AI can generate result, AI can optimize the result, and the optimized result can send back for AI to do the learning. Actually, if you're looking inside this circle, you find that actually we don't need the help of people. If our optimized algorithm is powerful enough, the AI can generate result, learn the result, and improve itself by itself. So maybe very quickly we can have some very funny thing or very interesting thing in the coming years. So okay, that's all for my presentation. Thank you very much.